Okay, so back to this graph again. We'll see here that, as I was mentioning earlier, the higher the energy of the bit to the noise ratio, the less probability of error, right? So you'll see that the probability of error goes down and down and down. So at this point, 4, for example, if I go up, the probability of error is somewhat close to 0.001, right? 10 to the power of minus 2. As the ratio goes higher, the probability is lower. All right. And the other information that the graph gives us is that actually there is a 3 dB difference between the probability of um, between the energy required to get the same probability if we compare, for example, amplitude shift keying relative to phase shift keying. What I mean is, for phase shift keying, if I pick this point here, right, and the energy that I need to have 10 to the power of minus 6 probability is 10.8, right? But the energy that I need to have the same probability goes up 3 dPs, which means that I need more energy if I want to use amplitude shift keying or frequency shift keying. Right? This means that phase shift keying is actually, for the same energy, gives us for the same probability of error, we need less energy. You can also look at it from a different perspective. Vertically, for the same energy, if I use phase shift keying, the probability of error is much less than if I use amplitude shift keying for the same energy, like if I look at vertically. All right. Okay, so using the information that I got earlier, right, I want to apply this to figure out what is the bandwidth efficiency for all of these techniques given a bit error rate of 10 to the power of minus 7 and a signal to noise ratio of 12 dB. All right, so first of all, where this equation came from, right? So we have, as we saw before, if I take the signal to noise ratio, if I take the dB value of this left side and the right side, what I end up with is this formula here. All right, so let me write it down. So the bit energy to noise ratio equal signal to noise ratio multiplied by the bandwidth divided by the rate, right? Actual rate divided by bandwidth. If I take the 10 log of both sides to get the dB, so this is E, this is the ratio in dB, and this will be believe it's a division. So I was right the first time when I multiplied. You can multiply it by b over r or divide it by r over b, you get the same result. All right, just making sure that we are not making any mistake. Okay, so now if you have 10 log 10a divided by b, that corresponds to 10 log 10a minus 10 log 10b, which is a dB minus b dB, right? So here, this is equivalent to signal to noise ratio in dB minus R over dB, right? So that's what we see here at the top. Okay, so this equation at the top came from this one. Just instead of the division here, because it's a log, so we replace it by subtraction. Okay, now what is the signal to noise ratio? It was given to us, that's 12, so we applied it directly. And I was given the error rate, 10 to the power of minus 7. So to get the energy to the noise ratio, I can go to the graph to this point, which here is clearer. So I go to, it's about 14.2, which is EB over N naught is 14.2. So now I have this, which is 14.2. I just need to figure out the ratio R over BT. So the ratio is minus 2.2. Okay. And so that's in dB. So to convert it to absolute values, I need to raise both sides to the power of 10. So now I have the rate over bandwidth equal 2.2 dB. Remember, in dB, this is 10 log 10 R over B. So what I need to do is divide this by 10 and replace, take the log 10 from one side So what I end up with is 10 to the power of 0.22. Right? And if I use my calculator here, I'm not showing you my calculator, but I'm doing it on the side. So 10 to the power of, oops, do this again, 10 to the power of 0.22 is 1.66. I did 2.2 instead of minus 2.2, so I only need to convert this. So actually, what I should have done is minus. So now I will get the correct result. It's not 0.66, instead of it's actually 0.6. And I got the correct result. So now R over BT is 0.6. The ratio, the rate, the bit rate to the bandwidth ratio is 0.6. Or in other words, the bit rate is 0.6 of the bandwidth. So if the bandwidth is 1 megahertz, then the rate is 600 kilohertz. Okay. And we can use the same example again. So now, if I was given the energy as 11.2, what is the rate? The rate will be 0.8 dB based on this formula here. And then do the same thing, convert it to absolute values, so I get 1.2. And so this is for PSK for the quadratic phase shifts. Actually, we get the rate that corresponds to the same bandwidth is much higher. I think earlier I said it's worse. It's actually better because we are increasing the rate, so we want more rate. We want more bit rate. So it's actually for the phase shift, for the quadratic phase shift keying, the rate to the bandwidth is 2.4. It's twice as much as the rate to the bandwidth here, right? Which what we want more bits transmitted for the same amount of bandwidth. I don't know why I said earlier that was worse. Remember here I said, yeah. Oh, I said worse because the bandwidth here relative to R. Okay, that's why. Yeah. Yeah, if you look at the bandwidth relative to R, this one is not good. It's yeah, not good, but the bandwidth that we need is lower, which is still good. Just I was looking at it from the flip side. Okay, so so far we talked about taking a digital signal and do modulation. So now we're talking about taking analog signal and digitizing it so that we can send it in binary form. Right? Okay, in this case, well, first of all, what kind of analog signal that we need to send? Most of our data nowadays is digital, right? But we still, the conversation that I'm having with you right now, my voice is translated into electric signal that's analog, but it has to be saved in a digital form. So it has to be converted into a digital form to be saved and sent and stored and all of that. So voice is one of those signals that are analog in nature, and they need to be converted to digital form. Okay. So one technique to do that is to sample the signal. And the slide that in front of you shows that, well, here's an analog signal. You can take any form, any waveform, and sample it, chop it. By sampling means measure the signal at specific intervals, and the interval has to be fixed in time, right? So I cannot just sample the signal at 0 second, then 5, then 13, then 11, or then 13, then 14. So it has to be fixed intervals, at fixed intervals, right? And then I measure the amplitude of the signal. So when you see at the bottom here, these arrows pointing up or down, these are the representation of the samples that I'm taking. So the first sample corresponds to the amplitude of the signal at this point. The second sample corresponds to the amplitude of the signal at this point, and so on. And you see here that these samples happen at fixed intervals. Right. Okay, but this generates a number, a real number, because the amplitude of the analog signal can be anything, right? So when I measure, the measurements can be any real number. Real numbers, I have to convert them into binary numbers, like 4.56 volts. I have to convert it into a binary form. To convert it into a binary form, we need to do quantization, right? So it's not enough to measure the data, but I have to measure it also in a quantized form. So I will revisit all these slides, but just before I continue, let's explain this in a different way. So I have my signal. Let's say this is the 0 level here, and this is the signal varying. Right? I want to digitize it, so I need to sample it at various levels. So I need to sample it here, here, here. I'll take my grid here as a way of sampling the signal into fixed intervals. So this results in different values, right? So this could be 5.2, this could be 7.13, and so on, right? This is maybe 7.10, right? And if I want to send this, I have to send it 5.2, 7.15, and so on. But these needs to be converted into binary. So instead of doing that, I could say, all right, if I want to convert this into an 8-bit number, right, or maybe use something simpler at first, if I want to convert each one of these amplitudes into a 3-bit number, right, then I have to divide my levels here, my amplitude, into 8 levels, right? So let's say level 1, 2, 3, 4, 5, 6, 7, 8. or maybe just considering that I actually have higher signal, so maybe my levels here, so this is the last one. Let's split them equally. So what I get level 0, 1, 2, 3, 4, 5, 6, 7, right? Actually, that's it, 7 levels. So now if my signal happened to be here, I cannot, when I convert it to a number, I have to choose whether I convert it to this level here or this one here. I have either the 0 level or 1 or 2 or 3 or 4 or 5. So that's all the levels that I have. So I have to convert it to 3. So I'm going to send 0, 1, 1, right, for this particular number. So again, if I take this part here, so this signal, it's closer to 4 than to 3, so I'm going to send 1, 0, 0. The one after it, it's probably closer to 5 than to 4, so I'm going to send 1, 1, 1, 1, 0, 1. This is close to 6, so I'm going to send 1, 1, 0. This is close to 7, so I'm going to send 1, 1, 1, and so on, right? So here I converted, this is my binary sequence that corresponds to the original analog signal. When I receive it, the receiver will take these numbers and convert them back, so I have the same levels here. So when I get 100, the receiver will put a mark here. Then when I get 101, the receiver will get another mark, put another mark. 110, which is 6, it's going to be here, and 7 is going to be here, and then after that will be the other ones. So here the receiver will be able to convert my signal back to its original form. So now with digitization, I need to do two things. The first one is called sampling. The second one is the quantization. Sampling is dividing the signal along the time, right, and measuring. And quantization is to approximate each measurement with one of the available lines or levels, quantization level that I have. Now you notice one thing here, or two, is that I couldn't exactly send the actual level of the signal. I approximated it to the nearest quantization level. This means that I introduced an error. So the receiver, right, it doesn't know what the actual level was. It's lost. All the receiver knows is these levels, 4, 5, 6, 7, and so on. So this quantization introduces an error called quantization error because of the mismatch between the actual amplitude of the analog signal and the quantization. Right? So that's one of the prices that we have to pay when we convert an analog signal to a digital one. Okay, that's the first thing I need to know. The second thing is I can improve the quantization and reduce the error by increasing levels. So instead of 3 bits, which allow us only 7 levels, I can have 4 bits, which will give me 16 levels. I can have 8 bits, which will give me 256 levels, right? So I can add more bits and get more accurate representation of the original signal. More bits means more data to send, right? Lower 3 bits, I can send the whole thing and see how many points I have, multiply by 3. If I have 5 or 8 bits, then more bits need to be sent. So the more resolution I have, the more bit rate I need to send the signal. Okay, so that's the general idea. Now let's go back to this is the quantization, and we're using 16 levels here. Now I showed you all the levels positive, but I can also divide the levels into positive and negative. I can do few improvements. One of them is let's say my signal moves slowly. It changes slowly, so it doesn't change very frequently. So I don't really need 3 bits or 4 bits or 8 bits to represent the signal. I can just say to the receiver the signal went up or went down. This is the only thing that I need to say. So this technique is called delta modulation, and the delta comes from like the difference. Delta is the difference between the previous level and the new level. So here, my analog to digital converter, what it does, it starts by saying, I'm starting at this level, and then when the original signal goes up, I am saying, well, the signal increased. Every time the signal increases, I'm sending 1 to say that the signal has increased. When the signal starts to go down, I lower, I say, well, the signal has increased, has decreased. So what I send is either 1 to represent the signal increased or 0 to represent that the signal has decreased. So this is what I send, ones and zeros. The receiver creates, every time it sees 1, it increases the step or increases the height of the signal by 1. Every time it sees 0, it decreases the signal by 0, by 1 step, by 1. Right. So if my original signal is this black smooth curve, my recovered signal will be this staircase signal. And you can see here that because the signal actually doesn't change significantly, my staircase goes up and down at the bottom here. Right? Now, one thing I notice here is the new signal that the receiver recovers is not exactly as the original signal. It's not smooth, it's a staircase, and it's actually lagging behind. There is a delay. Right? So there is an advantage and disadvantage to this technique. The advantage is I don't need quantization. Almost the sampling and the quantization happen at the same time. And I only need to send either 1 or 0. The disadvantage is the corresponding signal is the noise or the difference, the error from the math perspective, the error is high. right? So that's why this signal is good to monitor or to convert something that it doesn't change very rapidly. So if I am monitoring the temperature, for example, and I am sending the temperature to a monitoring station, the temperature doesn't go up and down very quickly, so I can represent it by a delta modulation. Voice, on the other hand, cannot be represented very well with a delta modulation because it can change very rapidly. Right? Another thing that's maybe missing here is I can have a nonlinear quantization. Speaking of speech signals sometimes they have a lot of details near the zero and not a lot of details at higher levels. So I can let's say this is like, for example, this is a signal that represent a voice. If I say, well, let's do quantization, an equal quantization, uh, bottom and up, I see that I lost a lot of detail. All of these points that if I sample them, all I get is either this level or this level, right? So all these small details close to the zero level are lost. So equal or linear quantization is not good for such signals. So what I should do instead, I should take this, I should increase the number of levels at the bottom, right, close to zero, and decrease them at higher levels. So here I may say, well, I am going to create more levels for these, for the close to zero, and then increase my levels otherwise, right? So here I increase my resolution so I can represent these minor or small changes near the zero level and decrease my resolution everywhere else. This gives a better representation of some of the signals that are not, they don't change the same way at all levels, right? So that's what we mean by nonlinear quantization or nonlinear encoding. All right. There is also very, very important um, a piece of information that we need to know. Right? I think, I don't know if it was mentioned in previous lectures or not, but we don't, we weren't told exactly how many samples we need, right? We we saw that we need to sample, right? Here we need to sample the signal, but how many samples we need? Let's see. If I come to this graph that I created earlier and say, let's delete all these samples here, right? And instead of sampling with every square that I have, I'm going to sample at twice the time interval. Will I lose much information? So the receiver will receive this, and maybe they will construct the signal back by connecting these samples. Right? Now, the blue line represents what the reconstructed reconstructed signal. The black line, the original line, is the original signal. Now, of course, the blue line goes along the same changes as the black, but it's not the same, right? There is an error. There's a big error here, right? There's a big error here. So you can see from this diagram that I cannot like just choose any sample. There is a limit. And also like the quantization, the more samples I have, the better the resolution, the better the accuracy of the signal. But what is the minimum sampling rate? Okay, so let's find out. We'll find out by using a simple sine wave as an example. So here is a sine wave. Let's say this is the sine wave analog that I want to sample it. And let's say I'm going to sample it at every line here, as I did before. So I sampled 1, 2, 3, 4, 5, 6, 7, 8, 9 samples, or 8, considering that this sample here will be the start of the new cycle. So I sampled 8 times, and if this is a second, then I will say the sampling rate is 8 times per second. Okay, and if I do the quantization and send it, what I will receive is something like this, which is very close to the original sign. Okay, great. Let's delete that. And let's try to sample it at lower rate and see what happens. So now I'm sampling it at the beginning and every other line. So I'm sampling it here 1, 2, 3, 4 times. This one corresponds to the next cycle. So I'm sampling it at 4 times per second. Again, if I connect all the dots by the receiver, so the receiver receives this value, this value, this value, and this value, and this value. So if I connect them again, I will get somewhat close, not as smooth, but the frequency is the same, right? The frequency is close by, is the same, since it's, if I continue here, I will get the same frequency, but the shape not really good. All right, let's decrease the sampling rate and see how much we can get away with it. Let's decrease it to only 2 samples per second. So where do we choose our samples? If I choose them here, if I choose my sample here and here, right? And considering this is a periodical signal, so maybe another sample here, another sample here. So when the receiver receives the signal, they may be able to construct something like this. So at 2 samples per second, I still Now, instead of nice sinusoidal wave, I get this triangle, but the frequency is the same. I still have the same frequency, which is 1 cycle per second. Let's go further and say I am going to sample only at, I'm going to take 1 sample per cycle. And I'm going to take the sample here. Now, considering this is a sinusoidal signal, so and periodic, so my second sample will be here, my third sample will be here, and so on. This actually would be impossible for the receiver to retrieve the signal, the original signal, right? Because all the points that the receiver will get is this one, this one, this one. If they're connected together, it's not going to be the same signal. It's going to be a DC. So it turns out that this is actually my minimum sampling rate. So for a sinusoidal signal with 1 cycle per second, I need to sample it at least twice per second to get the same shape. Now, how about the smoothness? The smoothness is another issue, but the frequency that I will get, it will be the same as the original. And in many cases, the frequency is more important than the shape. The shape, in some cases like voice, the shape of the signal, if it's not smooth, I will lose some of the accuracy. But if I lose the frequency, I will lose all the information. So we are more interested in receiving, in preserving the frequency. And to preserve the frequency, I have to have at least twice the sampling rate should be at least twice as the bandwidth of the signal. And in my case here, the bandwidth is 1 hertz or 1 cycle per second. And we will call this the Nyquist theory, right? So Nyquist theory, or Nyquist came up with this information. This turns out to be an important piece of information, because now if somebody says, okay, what is the minimum number of samples that you need for a voice? Okay, voice usually it's a limited, like we know from research that voice has a bandwidth between 300 hertz to about 3200 hertz. So that's the bandwidth of the speech, like signal. To be on the safe side, I may say, well, let's assume that the maximum bandwidth of the speech is 4000 hertz or 4 kilohertz. So to preserve the signal, to digitize it and send it without losing information, I need to sample it at least twice as much. So the sampling rate will be 2 multiplied by 4k kilohertz. So I end up with 8000 or 8k samples per second. And you will see in the examples and the questions, this is what we call the Nyquist rate. So if somebody says, what is the Nyquist rate required to sample 4 kilohertz speech, you will say 8000, right? And sometimes we'll say, okay, signal sampled at twice the Nyquist rate. So the Nyquist rate is 2 times. Twice of that means 4 times, right? So keep that in mind. So here we took a signal that's 4 kilohertz, sampled it at Nyquist rate, so we get 8,000 samples per second. And each sample, we represented it, we quantized it by 8 bits. So I have 8,000 samples. Each sample needs 8 bits. So 8 multiplied by 8,000, that's 64 kilobits per second. And that's the usual sampling rate for speech without doing any form of compression or anything like that. So this is pure, like take a signal, sample it, quantize it. And we'll call that pulse code modulation technique. So the pulse code modulation means we take the signal, sample it, and quantize it. So I mentioned earlier that the quantization introduces error, right? So no matter what I do, as long as I have fixed number of levels, I have to introduce errors because there will be never case where I can be representing a real number in binary. So I have to lose some of the information. So the signal to noise, we have a signal to noise ratio, and we have a signal to noise ratio due to quantization. We'll call it signal to noise ratio quantization. And it is given by this formula: 6 equals 6.02 n plus 1.76 dB, right? So the 6.2 n is the number of levels, or the number of bits actually. Yeah. Yeah, the number of bits. And if I know the number of bits, then I can figure out how many, what is the signal to noise ratio quantization. So this formula here shows that if I have n bits, n is 4, for example, then how many levels I need? I need 2 to the power 4, which is 16. If I take the log of that, multiplied by 20. So anyway, so again, um, if I explain again, so log 10 2 to the power n, this corresponds to, or this is equal to log 10, right? So this becomes a constant. And we will be able to simplify this by saying just multiply 6.02 by n and add 1.76 dB. Right? So if n equal 8 bits, what I end up with is signal to noise ratio quantization is 49 dB. Right? Here we go, the nonlinear encoding again. So I explained it before, so there is no need to explain it again. I don't know why the slides are not in the right order. This is the circuit that we need to do a delta modulation. So every time I'm comparing the, the staircase to the original signal, if I see that the original signal has a level higher than the staircase, I increase the steps. Right? Once the signal becomes less than the staircase, I start to decrease the steps. So the step's always lagging behind. Okay. And I'll use a comparator here to compare the original analog signal with the staircase. Okay. So pulse code modulation has a better signal to noise ratio than the delta modulation. Why is that? Well, obviously, because the delta modulation introduces a lot of errors. You see all of these, the difference here between the original signal and the staircase. It's a higher error. While if I use a simple quantization, I will be maybe quantizing the signal at these horizontal lines, and these horizontal lines will give me less error. Okay? So that's intuitively why. If the pulse code modulation can give me better voice reproduction, so it means that I can take the voice, digitize it, send it, then reconstruct the voice back. 7 bits usually good, 8 bits better. There are situations where I need to modulate an analog signal with an analog signal, right? So we talked about taking digital signal and modulate it initially, take analog signal, convert it to digital. Here is the situation where I have an analog digital and I want to send it as analog signal. One of the reasons I want to do that is what I mentioned before. I have a signal that's occupied the same bandwidth or some bandwidth, but I want to send it through another bandwidth. So I need to shift it. I need to send it in a different channel. So I need to modulate it again so that I can send it. So this is one of the examples. Sometimes sending it at higher frequency means that more efficient transmission. Sometimes I need it for multiplexing. So in the next slides, we will see three different approaches to that, which are similar to what we saw before. So if I take an analog signal like this one and multiply it with the carrier, I get something similar to the amplitude shift, phase shift, amplitude shift keying that I mentioned before. You see here I multiply the high value with the high value, or multiply the zero with the frequency, I get kind of zero. So the receiver can take this signal, take the envelope, take just the outer boundaries here, so it can retrieve back the original modulated signal. I can use the same signal, but one frequency, but change the shift. So here we're not actually changing the frequency, we're just changing the shift. So the small values correspond to smaller shift, high values here correspond to high shifts. So I end up with the signal that doesn't change in amplitude, but it changes in shift, phase shift. I can also use two different frequencies. So let's say the positive corresponds to one frequency, the negative corresponds to another frequency. So when the amplitude is at the highest, the frequency will be chosen as F1, when the amplitude is at its lowest, the frequency will be this high one. Now, of course, now we don't have a rapid transition 1 and 0 as we saw before, so the transition between one frequency and another will be gradual, right? So you can see here we started with one frequency at the middle and then changed slowly and gradually to a higher frequency. So frequency shift keying here, or frequency modulation here, using two different frequencies, looks like phase shift somehow, but it's not, because we have two different frequencies. To understand the modulation, you need to see, or you need to revise some of these equations that use the cosine and sine. Let me see. We are actually taking this is the carrier. This cosine represents the carrier. This represents our data, right? And if I multiply them together and using relationships, I will end up with different equations here. Now, not really interested in looking at these. Maybe we'll look at them later in the tutorial and see how we can understand these better. For those of you who are more interested in digital signal processing, we can look at these books, but you don't really have to. Okay, so that's all chapter 5, and we finished it now. There are some related information in chapter 17 that probably worth talking about. A different type of modulation that we need to look at. So I'll explain to you what the problem is, and then we'll see what we mean by the spread spectrum, right? So let's go back to our notes here and see one issue that we need to face, is if I have many people talking, everybody has cell phones nowadays, right? And we need to talk to each other, either using cellular technology or using Wi-Fi. These are two different wireless technologies. Cellular technology in particular is a good example for this, where, okay, these two needs to talk to each other, while these two needs to talk to each other, okay? And they need to talk to each other on a separate channel. Because if they're both using the same channel, they're using the same, let's say, channels are limited. So if they're both using the same bandwidth and the same channel, well, the information between them will be mixed and garbled, and nobody will understand anything. So obviously, for A to talk to B, we need to assign them a channel. And for C to talk to D, we need to assign them a different channel. so that each one of them, each pair will be happy talking to another without interfering. Now, we solved one problem, which is modulation. We said that, well, the A to B need to talk to each other using digital signals, right? And so are C to D. So each one of them will be modulated using one of those different techniques of modulation that we talked about. So we modulate the signal. So we modulate this using different frequency, C1, carrier 1, and this is carrier 2. So if this is the center of the carrier 1 here, and this is carrier 2 here, so A and B can talk to each other using this channel, and C and D talk to each other using a different channel, right? And there is no interference. Okay, but who assigns these channels? Assigning these channels has to come from a control, has to come from maybe the wireless tower that assigns these channels. Well, that's one way to do it, is before anybody talks to anybody else, say, well, I need to have a conversation, give us a channel so we can talk without interfering. Well, that's good, but that also means that a couple of things. First one is we need to have a management. We need to have somebody like automated management to allocate channels to everybody, and also make sure that not just allocate the channel, but make sure that the channel is being used and then deallocated and allocated to somebody else and all of that. Also, allocating a channel may not be useful or efficient, as we will see later when we talk about multiplexing. Let's say I assign a channel to AB, but AB don't talk. They just turn, or they're not using it efficiently. So I'll be losing some bandwidth for no good reason. Okay, so how about I don't assign channels to anybody? Instead, I'll ask each one pair to pick a channel at random. And say, well, pick a channel at random, use it, and then once you're done, leave it. We run into a problem if I do this. What if AB use a channel and CD use the same channel? Okay, problem. All right, so another solution is to say, use the channel, but don't use it forever. Use it only for a limited time, then switch to another channel. So here is, I'm dividing the time into slots, and I'm dividing so this is time, and I'm dividing my frequency into slots as well. And for each time slot, there is a certain bandwidth, right? So all of these boxes represent a bandwidth that's available for a specific time. So if these two pairs, AB and CD, start picking channels at random, so here's AB, pick a channel, and CD pick another channel, and then they switch AB and CD, and then they switch again, and then they switch again. So with any luck, they will be continuously switching different channels. Sometimes they will interfere, sometimes they will pick the same channel, and there will be corruption, there will be corrupted data. But for the most part, they will not be using the same channel. And each one of them will be happy talking to each other, right? And of course, there is another mechanism that makes sure that both A and B are using the same channel at the same time. Otherwise, they will be, one is picking one channel, the other one is picking a different channel. So there is another way to make sure that both of them are in sync. They use the same channel all the time because they want to talk to each other. So we'll call this technique frequency hopping, right? So in chapter 17, we'll talk about spread spectrum. And with the spread spectrum, there are two techniques. One of them is called frequency hopping, and the other one is called direct sequence. Frequency hopping is the one that I explained, which means that each pair, they will pick a frequency and then they switch to another frequency and another frequency. This technique was first used for a different purpose altogether. It was used actually for military communication, and for military communication, if the military picks one channel and starts sending data over that channel, well, the enemy, they can send high power signal on the same frequency, and they jam communication. So they prevent the other side from talking. So by changing the frequency all the time, it would be very hard for anybody to pick which frequency that the other side is talking and jam it. So it started by military application, and then it found okay, so this is a solution where I can assign frequencies to different pairs of people, cell phones, right? And each one of them will be talking without interfering with another. So I said earlier that they pick the channels randomly. They're actually picking the channels pseudo-randomly, which means that each pair follow a sequence that they only the two of them know, but from other people's perspective, it looks like a random sequence, right? But it's not really random. We'll call it pseudo-random. The other technique is called direct sequence. With the direct sequence, using the same principle, take the input 1010, that's our simple data, and multiply it with another sequence that looks random, and it's at much higher rate. So you'll see here that the rate is 4 times as high as the data. If you multiply these two together, or XOR them, so if you XOR them, so 1 and 1 is 0, 1 and 0 is 1, so you XOR them together. XORing, as you will see later in the next course, in the math course, XORing is one of the techniques that we use to do encryption, very quick encryption. The benefit of XORing is it's reversible. So I XOR the data with this random stream. I get C. I send it over the channel, and everybody else send over the same channel. All they use the same channel to send. But only the receiver can listen to the data by taking the received signal, XORing it again with the same pseudo-random bit, and by some magic of mathematics, Actually, this part is not really magical. This part is just simple XOR. So if I take the received signal and I XOR it, I'll end up with the same input. The magic happens in between. The magic happens when this actually signal don't interfere with each other. And even if they interfere, you're still going to be able to receive the signal correctly. So that part is not shown here in the slide, but it's part of the, I'll call it magic. It's just a very impressive math. So I will let you do these questions, and we can actually, some of them we'll do them in the lectures. Okay, so that is the end of chapter 5 and lecture 6. I will see you in another recording, so hopefully that's useful.